Hi, everybody. This is the Physics of Bitcoin show with Giovanni and Steven. This is episode 32. 32. Um, cannot believe it. 32 episodes. Again, a little introduction. This is a show where two physicists, me and Steven, um, we had an eclectic career where we studied as astrophysicists, both of us. We studied the sky, the universe. Then we went to other careers. I studied the brain, in particular the brain during sleep. Stephen was most on the computational field. But the idea is that we were both using physics concept, to make sense of a world, and it was natural when we both encountered Bitcoin to try to understand it in the same way using these tools from physics. And it was very successful because I think we basically got how Bitcoin works. I think we go deeper and deeper every week in this deep understanding of Bitcoin using math, using physics. The power law is our main guidance and main reference, but it's not just about the power law. We do a lot of other analysis. Stephen also started to do a lot of interesting analogies with physics concept. This actually give us a chance to talk about interesting concept in physics. So if you want actually to learn some concept, from astrophysics, cosmology, and so on, this is the show for you. And it's kind of cool to put Bitcoin in this context, that of being like another natural phenomena, basically. Even if it is driven by human action, humans are part of a universe. There have been other studies, right? One of our inspirations is Jeffrey West. They wrote this book, Scale. He a huge part of the book is studying human constructs like cities that do follow mathematical laws. This is what the show is about. What is also very interesting, and I pointed out this, that we do look at previous results, from other scientists, in particular the work of Sornet or maybe Jeffrey West, etc. But a big majority of what we discuss in the show are novel results. And it's pretty intense because almost every week we have some kind of new result, even if it is maybe a minor result. It doesn't have to be a breakthrough every single time. But I don't know, I cannot imagine of any other show on the entire internet and Bitcoin community where almost every week there is a new result, a new insight into Bitcoin. So it's a very unique show. I think it should be followed by hundreds of thousands of people. But, the people that follow us, they are chosen. You are the best. So we really appreciate you coming to visit with us. Do you want to add anything, Stephen?
Yeah, I just want to thank our quality audience for joining us today. I am going to, in my portion, going to focus on an astrophysics and cosmological analogy. And I think this is new. I haven't seen this before. And it's something that's really been tossing around in the back of my head for a couple of years. And I think I finally pegged it in terms of how dark matter and dark energy and ordinary matter relate to the three big generations of money. So that's what I've got for you today.
Fantastic. I cannot wait. Okay, let's then go ahead. Please, Stephen, show out the agenda and take over.
Okay, Microsoft Edge is trying to, there it is. Okay. Sharing. Okay, it's show number 32, September 10th in the US, September 11th, where I'm sitting. So I want to give an analogy for Bitcoin with dark energy. And this little graphic in the lower right hand, many people may have seen this because it's bounced around internet for years. And what it's showing is the 14 billion year history of the universe conceptually since the Big Bang. And way over on the left, it's got the inflation epoch that took everything to a very small macro scale. And then it's got a map of the cosmic microwave background, which is the green and blue and yellow thing. And that was at age, a little under 400,000 years, so quite a long time ago, but we still detect it. We've detected it since 1965. And then there was a period they called the Dark Ages before the first galaxies and stars formed. And we've pushed the frontier back between Hubble and the James Webb Space Telescope now to the first several hundred million years that we're detecting the first stars and galaxies. And then things have developed, following really at the gross scale, general relativity, and a very isotropic homogeneous universe that's well described by that. There's something called the lambda cold dark matter as the canonical cosmology. And then we found out only 27 years ago that this dark energy is very important. And so this kind of conical shape, you see it tipping up. And at the top, it says dark energy accelerated expansion. So we're going to talk about dark energy today that drives that accelerated expansion. So it's all based on general relativity, and that the only term we care about for this analogy right now is lambda, this cosmological constant. And then, of course, inherent is also matter. So we'll talk about the two forms of matter. And dark energy can have different forms, but this cosmological constant form is the simplest possible form, first introduced by Einstein. And it says that the pressure of this kind of dark energy fluid is negative, but in proportion also to the dark energy density. And there's this C squared that balances the units and so forth. Rho here is the energy density of the dark energy. So it's kind of an anti-gravity, basically, because the pressure is negative. It goes into the equations of general relativity, just like these other source terms that come from matter and have attractive gravity, but because of the negative pressure, it's a repulsive form. It was not in the original equations of general relativity that Einstein wrote out in 1915, but 2 years later, he added it in a failed attempt to create a static universe model. And it was quickly pointed out to him that that model was unstable. If you just perturbed it just a little bit, you'd either get a collapse or an expansion. So what's been learned is that with an isotropic, homogeneous universe, you're either collapsing or expanding. And then by 1929, we knew that we lived in an expanding universe, and we've been living in one, or it's been one of that type for 14 billion years. So I'm going to revisit for a little bit just the black hole Bitcoin analogy that I talked about last week, because I think both the black hole analogy and the dark energy analogy apply, but they apply in a different manner. The black hole analogy is more for the bubbles and the period when the bubbles were really important. And now we see that the bubbles and the volatility have been dying down. So what's the analogy for the long-term growth? And so I want to propose dark energy. And fiat, I'm positioning as dark matter, and I'll show you why. Now, in terms of how the universe is developed for 14 billion years, or 14 giga years, as I call it here, we're with Bitcoin, for the analogy, we're only at 2 giga years. So we're not at where we currently are for the age of the universe. It's as if we were at the early stages when it was only 2 billion years old, when we make the analogy with Bitcoin. And the reason is that the dark energy has to catch up to the fiat dark matter analogy. And it looks like we could catch fiat by mid-century based on the power law trajectory. So that's what I'm going to describe. And then I'm going to close with one little slide on doing regressions in block age, and this includes difficulty as well. And then show the latest log periodic power law fits for the bubble or the waves that we're seeing in 2025, and what's the sort of immediate outlook. Okay, so let me just revisit the black hole Bitcoin analogy. I presented this last week for people who were not on last week, but a refresher for those who were on. And so in the left-hand chart, I have on the y-axis the cosmic age running from 0 to 14 billion years, where we are at present. And then I've got the Bitcoin age running from 0 to 16.7 years since the Genesis block. So you can make this rough equivalence that a Bitcoin year is about 830 million cosmic years, if you just kind of assume linear proportionality. So if we think about that, then when Bitcoin was, say, 2 to 6 years old, it turns out that that corresponds in the cosmic time scale to when the supermassive black holes were showing the most activity. And when they're in their most brilliant, most luminous phases, what we observe are called quasars. And those peaked at around 4 billion years. So the right-hand chart and the yellow curve in particular shows the most luminous supermassive black holes. And of course, we're not seeing into the black hole, we're seeing the accretion disk that surrounds it, and we're seeing the infall of material that eventually falls past the event horizon of the black hole. But when it forms an accretion disk, it's very, very hot due to the strong magnetic field. It can be millions of degrees. And there's also strong magnetic fields, so it can radiate both in hot thermal radiation up into the X-rays, and it can radiate through what we call non-thermal synchrotron radiation, etc., because of the very strong magnetic fields. So if you look at that orange curve, what's on the y-axis is how many sources we see. It's the density, and that's a logarithmic representation. So it rises very rapidly during the first 3 to 4 billion years, and then it flattens out. And then it's been in decline ever since for these quasars. And they've dropped by a factor of 30 in intensity, because that's a log linear chart, by the present age on the right-hand side. So just that general idea that these quasar events, which are actually intermittent, they're not turned on as very bright quasars all the time. They'll have these bursts, and when I say bursts, I mean tens of millions of years of rapid infall of usually leftover gas from the Big Bang, primordial gas, we call it. And then eventually you build up enough luminosity and radiation pressure and thermal pressure that you inhibit further accretion for a while. And then it's quiescent, and then you get another burst. But the general point is that it's been in decline. If you look at the blue and green curves, those are the low and moderate luminosity supermassive black holes. We call them active galactic nuclei as we detect them, AGNs. And in the lower left, that little image is from the James Webb Space Telescope of 4 of the earliest and most distant of these active galactic nuclei. We don't know exactly what's going on, whether it's star formation or whether it's an active galactic nucleus around the supermassive black hole that we're seeing. They call them little red dots. They're at very high redshifts, which means very early times, really less than 1 billion years for most of them. So that's about as far as we can see back. Okay, so the idea is that with the black hole analogy, these supermassive black holes and their quasar activity, and Seyfert, which is for more moderate ones, that they're still there, but there's less infalling material that's powering their accretion disks, and so their luminosities are much lower, there's less flaring, there's less of these kind of bursty behavior. Just like the supermassive black hole at the center of our own Milky Way, which is not that large. It's only 4 million solar masses and intrinsically not so luminous. It's closer to a steady state. It has a lot of variability in kind of absolute terms. factors of 10 and 20, but the overall luminosity is not that high. So you've got a more consistent, slower inflow. So the question is there another astrophysical analogy that can take over as we're entering into a somewhat more stable era with not so much bubbling as we've seen in the past? And so I'm proposing dark energy. And one of the things that's going on is that the institutional Bitcoin holdings have become dominant. In fact, 3/4 of the net buying this year has come from the treasury companies, Strategy and others. And most of, the next largest class is the ETFs. And there's been net selling by retail, particularly some of the large whales have sold. And private companies and governments have not been net contributors. So it's really been institutions in those two categories of treasury companies and ETFs. And their behavior is more steady and long term. And so this dark energy analogy may be more appropriate. Okay, so I'm showing you a simplified version of the equations of general relativity in that first line. There's no quiz, you don't need to learn it, but it just has these are tensors. And so actually each one represents...
Wait, I thought we have a quiz at the end.
There'll be one question at the end. No, the only quiz will be your commentary as we, kind of phase out towards the end of this. So that R thing is, it's just a 4x4 matrix. It measures the curvature. These are called tensor equations. There are 16 of them. There's symmetry there, so they reduce to 10. There's a little g, which is the metric. And then the big G, the capital G, is just the usual gravitational constant that you have in Newtonian dynamics. And then T is the energy tensor. And then the only thing we care about right now is this lambda, which is bolded, capital lambda. It's called the cosmological constant. And the way you can put it either on the left-hand side or the right-hand side of the equation. It's often written this way with it on the left-hand side. But it's an energy term and it's got pressure terms, so you can put it on the right-hand side inside that T. But we break it out here so that we can talk about it. And it represents the simplest form of dark energy with negative pressure. So P is pressure, rho, that thing that looks like a P, small p, is the dark energy density, which is positive. And then there's a C squared. And in general, it could be not -1 times that expression. It could be -2/3 or, some larger number, more negative than -1. Observations suggest that it's very close to -1. There are arguments about whether it's very slowly evolving and slightly different. We don't need to go into those. It's so close to -1 that, we can look at the simple form for this. So the anti-gravity idea is that it's due to the pressure, and there are actually 3 components of the pressure. And when you put it into these equations, they end out outweighing the energy density. So the negative pressure is what causes the universe to have this repulsive force due to the lambda, and has caused the accelerated expansion over the last several billion years. So Einstein put it in the equations in 1917 in an attempt to create a static solution. He failed to create that. He then called it his biggest blunder, but it turned out he was correct. And in 1998, the observations were made with distant supernovae. There's a certain kind of supernova called 1A that occurs when you have a white dwarf that's right at the limit of quantum electron support. We call it quantum electron degeneracy pressure. And if you accrete a little matter onto it, the support is overwhelmed and it goes into supernova. And because they're all the same mass, 1.4 solar masses, they all look the same. They have the same luminosities and light curves more or less. And so they can be calibrated. And we know their luminosity is absolute, and we can use them for distances. And then when you produce this plot that was first created by Hubble in 1929 to show the expanding universe, you find out that these supernovae are further away than expected. Well, what could cause that? It appears that dark energy is what caused them to be further away than expected. That is, to drive a faster than expected expansion in the universe.
I went I went to a conference where the two groups agreed finally, because for some time we were not agreeing. We had the two ages of the universe that were pretty different, almost by a factor of two. Even if my astronomy professor, I don't know if they say that at Harvard, where you studied, they were always saying, "Oh, it's just a factor of two. In astronomy, a factor of two is nothing."
Well, exactly. I mean, when I was in graduate school, we didn't know if the density was 10 or 20% of the critical value or 100%, right? And we didn't know the value of the Hubble expansion parameter to within a factor of two. And then by the time we got the very good cosmic microwave bound measurements and then this result, things had been more nailed down, and the expansion parameter ended up being the geometric mean of the two extremes.
Exactly.
And these two teams that were, trying to compete with each other, right?
Yeah, one was in Australia and the other in the US.
Right. One was at UC Berkeley and the other in Australia, and they ended up, confirming each other's result, and so they shared the Nobel Physics Prize.
This is how science works, by the way. This is a very important lesson, that you can get sometimes divergent results, but if they are dealing with the truth, eventually they converge. It's a very important science methodology example.
And we always need confirmation, right, from some other set of researchers.
Yeah, exactly.
In order to have high confidence. And okay, so here's what the mass energy balance of the universe looks like right now. The black is dark energy, and it's 69%. And we do the equivalence, we use E equals mc squared to show the equivalence with matter. And there are two types of matter, the normal matter and the dark matter. And there's 5 times as much dark matter by weight, by average density, as normal matter. And then I've labeled these gold, fiat, and Bitcoin. And I'll show you why in a moment. And it's actually the order in which we learned about these things, just as same as the order at which these things were money. So first we knew about normal matter, then we knew about dark matter, and then we knew about dark energy. And it's the same with gold as money, then fiat, then Bitcoin. So this is determined from many experiments and observations and multiple techniques: the cosmic microwave background, the galaxy separations, the pattern on the sky, particularly the large scales, the recession velocities, the supernovae distances, X-ray clusters of galaxies. They all give the same
8-9 pieces of evidence, right? That all come together.
Yeah, the helium abundance stuff, cosmic nucleosynthesis.
Yeah. It's kind of crazy, though, that only 5% of what is there is what we know. Everything else, we have no clue, basically.
We have clues, but we don't know precisely what they are.
Yeah, some clues, yeah.
Our clues are gravitational.
Yeah.
So you and I and everyone's made out of normal matter. We call those baryons. And that's just your protons and neutrons, and then the electrons that, sit around the atomic nuclei. And that's what that 5% is, and that's what stars are, etc. Now, in the early history of the universe, dark matter would have dominated. So it's only the past several billion years. I'll show you the curve for that. And it doesn't matter whether we measure the dark matter density at the edges of galaxies with the extra gravitational effect there, or whether we measure it in clusters of galaxies where it dominates how fast the galaxies zip around inside the cluster, or whether we measure it in the cosmic microwave background from the details of the distribution of these very tiny density fluctuations of only 1 part of 100,000 that we see in the microwave background, and it became the seeds for all the structure that we have today. And what's key is both the normal matter and the dark matter thin out in the same way as the volume grows. So if I imagine a sphere growing and I increase the radius, the volume goes up as the cube of the radius, and their density drops in the same proportion. Now, we live in an overdense region. We live in the solar system, in a galaxy, and local group, and that's all gravitationally bound. So that part's not expanding. But the expansion happens between clusters and groups of galaxies at the largest scale. Dark energy is different. It does not thin out. It's intrinsic to every volume of space. It may be due to the vacuum energy of each unit, each square meter, cubic meter of space. This curve shows how that parameter, lambda, evolved over time. And here we call it omega sub lambda. And omega sub lambda is just a fraction of the total mass energy on average in the universe due to this dark energy as a function of time. And so you can see that early on it was very, very low. And right now, where that little shaded box is, and it says Z equals 0, and that's age 13.8 billion years. And you can see it's got a value of around 0.7. And it only became dominant, across the 0.5 value sometime after age 10 gigayears, 10 billion years. And I've plotted a little bit of the future, the next 5 billion years. That's the trajectory into the future. And actually, 5 billion years from now, it'll be more than 90% dominating. So dark matter dominated in the first 10 billion years. That was the history. The ratio with ordinary matter was always about 5-1, we believe. The size of the universe, we parameterize that by this redshift, Z. And so that's just a scale factor. The dark matter density drops is the cube of that scale factor. So that's just a 1 over volume effect. The dark energy density is constant. It's an intrinsic value, intrinsic to vacuum space. And it's actually a very small number. It's 4 GeV per cubic meter. And a GeV is the rest mass of 1 proton. So it's as if you took a cubic meter, you only put 4 protons in there, and then you pulverize them into the pure energy and spread it out in that volume. So it's very, very tiny, but space is so huge. And then the pressure gets a factor of 3 and is negative, and that's what causes the expansion that occurs between the clusters of galaxies. The clusters themselves are gravitationally bound. The crossover was at cosmological epoch in what we like to talk about, redshift 0.3. So if you have a galaxy, the light would be shifted by 30% to the red. If it's, you look back to the time 10 billion years.
It's not just an expansion, but it's an accelerated expansion.
So it's an accelerated expansion because, once we got to the crossover point, it's heading towards what we call a de Sitter solution, which is basically going to double every 11 billion years in scale in each dimension, which means the volume goes up by a factor of 8, 11 billion years. So you can work out, 100 billion years from now, that's a huge expansion.
Yeah, because that is a strange result, right? That people didn't expect until the last 20 years or so, because this is why, so the more natural state for the universe will be static, where nothing changes. Then this is why Einstein introduced that factor, or maybe slowing down because actually gravity attracts, right? So
static is not a natural state. Static is it's not
disallowed
by general relativity.
Newton and all the other, in fact, even Einstein. Let's say it's the lazy lazy solution, lazy
The
solution.
lazy solution is eternal and static.
Yeah.
That'd be Newtonian, you know.
But then you can assume, okay, maybe because of gravity, and there was this initial explosion when gravity slows down things, and then it should actually slow down. Instead, you will not expect that the expansion is accelerating. That is weird.
Right.
But
It
the
is a
data
really,
is data. Data is data.
it is data. It's a
You
really
know,
surprising result.
yeah,
You
you
know,
have to accept
somebody's
the
published
data.
a paper that said, well, we're being fooled by the voids and so forth. But I don't think people take that too seriously. I've read the paper.
Yeah.
Um,
And again, it's a lesson, for what we do
yeah,
with Bitcoin. That whatever the data says, the data says. I
yeah.
mean, once you check it, double check it, triple check it, and you have many different pieces of evidence, you accept the data. Whatever that says.
So for Bitcoin, I'm not saying that we're where that little shaded box is. I'm saying we're very early on this curve
Hmm.
at around 2 billion years. So here's my larger analogy.
Okay.
So let's look at the graph. It's got a blue line, which is dark matter.
Uh-huh.
It's got a yellow gold line, which is ordinary matter. And then it's got a green line, which is Bitcoin.
Okay.
And the dark matter and the ordinary matter lose out as a percentage because they're thinning out with the expansion inversely with the volume. Their density is going inversely with the volume during the expansion. And so dark energy becomes more and more important until it crosses over at about age 11 billion years. And it has to
What is
cross.
volume here? Volume, uh, the economy, the total economy. What is volume here? What
Uh,
it represents?
this, okay, so this graph has on the x-axis cosmic age linearly,
Yeah.
and it has a linear y-axis, which is just the fraction of the total energy. So it would be the fraction, one could say, of the monetary system.
Yeah.
And right now, it's very interesting that, the dark matter to ordinary matter ratio is 5-1. Well, it turns out that the fiat M2 ratio to the value of all gold is about 5-1.
Mm-hmm.
So that's an interesting coincidence because
It
gold
is.
is a little over 20 trillion and fiat is a little over 100 trillion.
Uh-huh. And
Now,
okay, let me
yeah,
ask you why. It's an analogy, so analogies sometimes they hold up to a point and then they break. But why will you associate fiat with dark matter? What are the similar properties?
okay. Yeah, I will show you the details of that on the next slide.
Okay,
So let me defer that just a bit.
sure.
But think of gold as tangible,
Mm-hmm.
material, 1.0 money.
Yeah,
Think of fiat as less tangible, right?
yeah,
So like dark matter in that sense.
yeah.
But
It's
I'll go
it's
through the,
difficult to put it together
yeah,
because even if you calculate all of them too, then okay, what is really the money that is circulating? There are different type, but yeah, I can see. Yeah,
this
yeah.
is, this is,
It's
this
more
is,
abstract. It's more abstract.
it
Yeah,
is abstract. I mean, there's not a precise formulaic correspondence.
right.
This is an analogy.
Yeah, yeah.
And, the red X marks where we are now with Bitcoin, which is
Okay.
2%, right? 2% of what fiat is, or
Mm-hmm.
fiat plus gold are. And so in order to fulfill this analogy, it needs to grow as we expect it might
Yeah,
in terms of Bitcoinization of the economy relative to fiat. And certainly the power law trajectory takes it there, right?
right.
And it takes it there, mid-century. And so around mid-century, it would get to the crossover point is the general argument here.
All right. So for the growth of Bitcoin, you use the power law, I imagine, as an equation, right?
Yeah, I'm going to show that on the next
Okay.
slide.
Okay. Sorry.
Okay, so let's just go kind of the pros and cons of the analogy, at least how GPT-5 reacted. Dark energy is a mysterious force driving cosmic expansion. Bitcoin can be seen as a hidden driver accelerating financial system change.
Mm-hmm.
Dark energy grows more dominant with time. Bitcoin's relative importance is compounding, adoption, and is outpacing fiat monetary expansion. And it conveys inevitability. The cons are that dark energy is kind of this smooth, uniform background, probably. Bitcoin is more structured, meta network. And then it says dark energy accelerates everything apart. Bitcoin pulls adoption into a cohesive network. And then just comparing to the black hole analogy, that was more vivid for the adoption dynamics and capital inflows. And you can't leave the black hole once you cross the threshold. But the dark energy analogy works better for the sort of long-term inevitability of move towards increasing presence, shall we say, of Bitcoin and possible dominance.
Mm-hmm.
So the key takeaway is that fiat thins out like dark matter and ordinary matter, and they lose value relative to the real wealth in the world. Bitcoin, like dark energy, does not. It's actually growing value relative to, houses and businesses. So gold is like matter, fiat's like dark matter, Bitcoin's like dark energy. So ordinary matter like gold, it dilutes. It was the first one known. Humanity used it for millennia. It's touchable, tangible. You can weigh it. It's limited but not dominant. It's only 5% of the universe, and it's small compared to fiat. Fiat money 2.0 dilutes also. It's elusive but pervasive. It's ledger entries because it's mostly digital ledger entries, but it runs the economy, it runs the world today. Most of it's hidden in plain sight. You can't see the physical stuff. The paper that circulates is a small fraction. So in a sense, you're only seeing its impact, kind of like you only see the gravitational effects of dark matter. And it provides an overall stabilizing framework, just like dark matter halos stabilize the galaxy and cause it to spin faster, observed on the outer edges. So economies rely on this sort of fiat scaffolding, and they also rely on, liquidity and collateral, which is all based on debt, etc. So something that's, somewhat fictitious, right? Dark energy is actually more real than fiat because it's rooted in energy. It's rooted in precise algorithmic creation with, cryptographic math that runs on real hardware. And it's literally minted through energy expenditure. And the analogy with dark energy is the expansion, the accelerating influence, and Bitcoin's adoption curve and network effects have an accelerating quantity. It's mysterious, yet it's very important. Dark energy wasn't suspected until late in cosmology. Bitcoin didn't come around until, late in history, but may end up dominating. And this kind of anti-gravity effect, it resists capture by centralized gravity wells. We can think of the banks and states as the galaxies, right? Where the centralized gravity dominated by dark matter holds those galaxies together, but meanwhile, they're all being pushed apart by dark energy, which is dominating the total dynamics of the universe. So gold is a tangible anchor into atoms, fiat a scaffolding into gravitational wells and balance sheets, and Bitcoin energy-based driver of expansion and transformation. Okay, so that's basically it. I will hand it over to you in case you have any comments or questions.
I like the analogy. I think it's very cool. Now, what about? Are you writing some equations for? How did you draw these graphs?
Okay, I've got. Well, this is actually the universe, right? So
Oh,
those are
okay.
just the equations of general relativity. I
Okay.
do have
So you
I
didn't
do have in a
draw.
couple of slides. I have a different equations that is the power law. So I'll show that in a second.
Because it would be
Now,
cool to, beside the analogy, to draw three curves like that, but with functional form of what
yeah,
you expect.
I've done that. I'm going to show you that.
Okay,
Okay. But I think there's more work to do, but I'm going to show you what I've
sure.
done so far. Now, I also wanted to mention, because we had this discussion about black holes last week, is the speculative work that's being done that perhaps these black holes have dark energy cores. So that's kind of an interesting thing that ties the two phenomena together. This was first proposed by a Russian physicist in 1966 by the name of Gleiner, or Gleiner, I'm not sure how you pronounce it. But more recently, it's been revitalized by Kevin Croker, who was at Hawaii when he published this and is now at Arizona State and maintains some relationship with Hawaii as well. And he has modeled how the masses of supermassive black holes could grow over cosmological timescales if they couple to the background field and the background solution for general relativity. It's really kind of wild. And so he claims that they've observed growth of mass, growth of these dark energy cores that exceeds what you expect just from the accretion events. It's a little bit of a sideline, but it's kind of ties
It's
those
a
two
power.
down.
It's a power law. That equation is a power law.
Yeah, it's a power law. It's a cube.
Yeah.
And we have prospects, for getting better observational results. We talked last week about LIGO, which is the two facilities for gravitational wave detection in Louisiana State, Washington State, and their counterparts in Europe and Japan. And the proposal from the European Space Agency is to put something in space called LISA. And it would have much longer arms. Instead of 3 to 4 kilometers, they would be 3 million kilometers. There'd be 3 platforms, so there would be 3 arms. It'd be a triangle. And the whole thing would just follow behind in Earth's orbit, like 20 degrees behind, which is, a few weeks. And this is going to allow us to learn a lot more about.
It's a place where the gravity of the Earth and the gravity of the
It's
Sun
not. It's not.
balance.
No, it's not a Lagrange point.
Oh, it's not. We are not putting
No,
it in Lagrange.
it's just following behind, and it's just in the same orbit with the Earth, but following behind.
Okay, I thought they were going to put it in the
No,
Lagrange.
it's not in Lagrange.
Okay,
It's 20 degrees behind.
I see.
So this is going to allow. We have not been able to detect supermassive black holes from their gravitational waves. The ones that we've detected have all been intermediate mass, low to intermediate mass black holes. But this will operate at much lower frequencies, instead of hundreds of hertz, down below 1 hertz. And so we'll be able to detect maybe supermassive black holes swallowing, large amounts of material. And then it's going to tell us hopefully more about dark energy as well.
Yeah.
Okay, so here's the curve I think you're asking for, and this is just the catch up to fiat. So the blue curve is global M2, it's growing at 7%. And then the orange curve is Bitcoin, and the crossover is at age 44. So the Bitcoin share is just a power law, but then you have to correct for the exponential growth of the M2. And the equation shown at the bottom in italics. And so at age 44, which would be in 2053, you'd get equality with the future global M2. And that would be sort of like the 10 billion years for the universe in the dark energy analogy. And now we're only, 2 billion years in. And then that would take us to a sort of hyper Bitcoin or Bitcoinization situation where private open source money would be equal to the total amount of government money in the world. And of course, we would be ahead of any individual nation's M2, whether it's China or the US or whether it's the euro, much earlier, right? When we get to, say, the 25% to 30% range. And that will happen around 2040. So the trajectory we expect is that Bitcoin catches up to gold, when it grows a factor of 10 from here, and gold is going to grow too. But, when it gets to the sort of 10%-ish area to the 20%-ish areas when it might catch gold. And then when it gets to the sort of 25 to 1/3 area, that's when it could catch any of the three largest state currencies and become really, really important, particularly for international finance, global finance. And this is kind of the same thing again, but mapped on to the cosmic age, saying that, in 2025, we're down at 2 billion years effectively, and 2053 will be at 10 or 11 billion years effectively. And we're kind of seeing this thing as inevitable. This is the path that it could proceed on. Once lambda, the dark energy, dominates, the expansion accelerates forever. Bitcoinization would dominate the monetary base and dictate the unit of account as the first absolutely scientific standard for money in history.
Yeah.
Okay. So that's that portion. I've got a couple of other things to close out. I used to often do regressions against block age, and I haven't done that in a while, and I wanted to just go back and see how that was doing and revisit that. So I recently did this. I just took the data points at each difficulty adjustment every 2016 blocks. And so the power law index that you get with ordinary linear regression is 5.5 for price versus block age. That's shown in the upper left chart. So that looks familiar to people. And the R squared very high, 0.96. But it's a function of, it's a log chart in block height rather than in calendar years. And then if you do quantile regression, you get 5.66. So it's not that different. And the numbers are a little lower because we're now at block year age 17.4. So we're, 3/4 of a year further along in block year terms. And then if you do difficulty versus block height, I get 9.3 with ordinary least squares and 10.4 with quantile regression. Again, a very good R squared. The thing starts out at 1 because Satoshi arbitrarily just set it to 1, and it just, sat there for a while until the hash rate picked up, and then it, pretty quickly got onto the curve.
Mm-hmm.
And if you do difficulty,
you could throw away that data, maybe.
Yeah, you can throw it away and redo it. I did it for this one. And then the price versus difficulty that Giovanni has talked about a lot in the past, it's incredibly close to 0.5, 0.49 with ordinary least squares, 0.50 with quantile regression. It's the lower right chart. It's kind of amazing.
Yeah, it is amazing.
And, price as a square root of difficulty is the same as difficulty goes as the square of the price. And I think the general idea is if you didn't have technology progress and they were just competing with each other, difficulty might rise linearly with the price roughly, but we've got rapid improvement in technology that's, faster than even the halvings, right? Because the halvings only drop the reward by a factor of 2 every 4 years.
Yeah.
Moore's law, is you double every 2 years in underlying ASIC technology, and so you win that race, and you also get machines that are more efficient in their energy usage, and so that gives you another factor, and you end up with difficulty going as price squared.
Yeah.
Okay, so that's that, and then on to the latest log periodic fits. This one I just ran this morning, but the chart is from a day or two ago, but the numbers that I show on the left are from this morning's run. It's morning my time, which is, tonight in North America. And the upper chart, this is a little over 2 years, and it shows the sort of 40-20-40 split, color coded, for whether you're above or below the line mostly. And it shows in dotted line the log periodic power law fit. This is a log linear chart. And then that dotted line is the same as the orange dashed line. In the lower chart, with a 1 sigma uncertainty band around it. And it's a pretty nice fit. And it says that we're going into April before we would hit a critical date on this longer time scale, and the price would be around $177,000 at that time. Now, these different charts on different time scales do not agree. So this one is the 1-year run. I did not update this. It's a couple of days old. But it didn't change that much. I actually updated the numbers, and it's September 14th. So next week, it's saying there's a critical date. The uncertainty is 6,000, and it's saying a price would be 118,000 at the critical date. That 109 line corresponds to the 11.6 on the log price on the left axis. So it's a little above that. And then the one in the middle is the 4-month chart with 4 hourly data. And it says there could be an upswing into November, and that would take you up to the 131,000 area. And then the last one, the 1 month, is an anti-bubble kind of thing, because it's been on a downslope, during that interval. And it projected a pretty strong drop down to about 93,000. Now, one can imagine a scenario that's consistent more or less with all these charts, that we could have some turbulence that takes us below 100,000, through the rest of this month and into early October, but that we ought to get a pickup. The 4-month one says, well, we don't think it'll go that low, but it could have another downdraft, but then pick up. And but then we have this question mark about the 1-year run. So the longer term looks quite optimistic, but we've got some uncertainty here, particularly during September. Okay.
Very cool.
That's it.
Thank you so much. Okay. I will do my part. Let me find what I want to share. Okay. Let me see if I can do the optimization. All right. Hopefully this is bigger and you can see it. So I'm going to continue. We started last week. I'm in this kind of rabbit hole of looking at the returns, these things that they call the normalized returns, right? So basically returns is actually one of the most studied parameter in finance. You can understand a lot of things about an asset by looking at the returns. Usually returns are constant in most of the assets because they are exponential. So an exponential is a process where your returns are constant, right? So for example, if you have a bank account that makes like 5% a year, you're compounding this interest over time, you're going to get something that looks like an exponential. In Bitcoin, we know by experience, right? Because if you have been around even 5 years ago, you know that the returns 5 years ago were higher than the returns now. If you have been longer than that around, you know that early on, it was easy to get 1% a day with Bitcoin. Now it's much more difficult to get that. So mostly, we need to clarify. Many people think that diminishing return has to do with the bubbles, but no, it's actually the entire behavior of Bitcoin has diminishing returns. So I explained before that we can try to understand the returns by assuming we have a power law. The power law has this form, and then you can calculate the returns as a difference. I like to take the ratio. So basically, if you focus on daily returns, is the price today over the price yesterday. If you do a little bit of algebra, you take the ratio of two equations like these at different points, T2 over T1, you're getting this expression. And we know this quantity will go down in time. Why? Because T2 is, in fact, in particular, if we are focusing on days, right, will not be anything else than T1 plus 1. And as T1 becomes bigger and bigger and bigger, adding 1 to T basically is now a big difference. So this quantity, as T becomes bigger and bigger and bigger, is going to come closer and closer to 1. So you immediately see that this expression means that the returns are going to approximate 1. That means no returns when expressed as a ratio. So 1 will mean you don't go up, you don't go down, right? It's going to take a long time. I just calculated a few days ago, by 10 years from now, we are going down to something close to 22%. And by 20 years, it will be more like 17%. So it's no, today now we are at 45% a year. It's going down, but it's going to go down slower, right? So this is why there is not a big difference between the returns 10 years or 20 years from now. It's going to kind of stabilize around that value for a long time. But right now we are decaying. So the question is there a quantity that we can find that doesn't change, that in average stays more or less the same, right? It can fluctuate, but it fluctuates around a particular value. So that quantity, so it's easy to see, right? You can immediately look at these and say, oh, I think I have an idea. So the idea will be if I take the logs, and again, logs of a return is actually the preferred quantity that many economists or finance people look at. If you apply this simple rules of logs, basically it says if you take the log of a quantity like this with an exponent, the exponent goes down, right? Now you have basically a linear relationship between the returns and this quantity. But it's a deterministic quantity. It's a formula, right? This changes because the returns change all the time. They oscillate, but this quantity depends only on time. It's an equation, but it's very surprising, right? That you can actually write an equation that determines what the returns should be in average. So if I divide by this quantity, right? If I divide log P2, P2, P1 by this quantity, that in this case I've wrote the daily return. So it's basically T itself plus 1, because tomorrow is nothing else and today plus 1 day, right? I should get at least in average n, and then it's supposed to be a constant, right? If this hypothesis that Bitcoin follows a power law is true. So let's see if that is true. Well, these are the data for all the returns. So basically price. So these are the logs, right? Price today over price yesterday. You take the logs, you get this. It seems flat, but actually, if you zoom in, it's not flat, right? Maybe I should calculate like kind of a moving average to show you, but it goes down. These early returns were really big, and now we are going down. And the red curve is actually the theoretical curve. This is what is calculated from the power law. And you can see it does represent, it looks like some kind of average behavior of these returns. If I divide, and these I explained these, right? We can divide, we get these, and then it's very surprising because we get this. And you can see in this graph, what is missing is a line showing the average value. The average value is 5.9. That is familiar because that is the global slope. So these are kind of like, you can call them local slopes or daily slopes. It's almost like you're fitting every single day with a power law. And the values of these exponent can be really different, right? They can go all the way to 400 to minus 400. They kind of oscillate around the mean, but it's really cool to see that the mean is 5.9. So basically, it's really interesting. Is a power law. I need to look at other cases like this. Of course, even when you look at Claver's law or the other power laws, they are never perfect, right? The data points are all around a regression. They are not falling on the regression. So every power law is a power law in average. But this is in a different way, in the sense that there is a process that is producing this random data, but they distribute in this way around a mean value, and that value is the power law that we are familiar with. And this is interesting because you get a power law in average, but then you get variations, and that are all these oscillations. Now, you need to understand better where the bubbles are in this distribution. I suspect that maybe this bump here, there is an excess of values, but it's something that I didn't do yet. We can kind of color code and say where are all the and maybe these are the minima, right? The bottoms. So it doesn't follow a perfect theoretical curve. There is an excess here, an excess there. So maybe these are the bubbles, but I need to explore that. I am not there yet. But if you ignore these small little deviations, then you can find a theoretical curve. I try different. Gaussian doesn't work very well because basically Gaussian has small tails, right? It's fat in the middle and small tails. The real distribution seems to have like huge big tails. So you can look for other distributions. Gaussian is what people call the bell curve. There are many other type of distribution that fit different kind of phenomena in nature. I tried Lorentzian, Laplace. There are different calculations that you can do to see. It's not just by look. You do test to see which one is the best distribution. It seems what is called T location scale, it's the best. In fact, actually, many assets follow a T location scale. And the cool thing about that, once you say, okay, I'm going to approximate, I'm going to use this distribution. I can calculate the mu, right? It's T location has actually 3 parameters that determine how fat the tails are, how spread the data is, and then the average. So use these values, and then you do what is called a Monte Carlo simulation, that is basically kind of almost like a game where you throw a dice many times, basically many days we have since Genesis block, and it's a fancy dice that behaves with that distribution, has the same property. So every data here is almost like creating a Bitcoin day. Then you put them all together to recreate a history of Bitcoin. And some of these history are crazy because there is, in some parallel universe, a Bitcoin that went all the way to $10 billion. That because it was very lucky situation where you had a lot of winning date relatively to losing dates, and you got this crazy value here, right? $10 billion Bitcoin right now. Then you had universes where Bitcoin didn't succeed for some reason. And so you got a lot of bad rolls and Bitcoin is just a fraction of $1, like 10 cents or something like that. But you see, you do it, you can do this millions of times if you want. And so I color coded the density, so how many of these paths are close together, and green are the denser one, that means the more likely and probable one. And then the coolest result that I was very excited when I got this is that the median value of all these paths is the power law. So it's basically, you create the power law, you reproduce the power law result without doing any regression, just by looking at the statistical property of Bitcoin. It is really, really cool. It tells us that this power law is not some kind of, you're not, many people have doubts about the fitting. It doesn't, they don't understand it, but these should destroy all the doubts. We are recreating Bitcoin by normalizing the returns with some function that seems to make it time independent. Then you recreate the returns by multiplying by that function. So basically, it's a deterministic factor that tells us there are diminishing returns. And then just by looking at the statistics of how the gains are distributed, you reproduce the power law. I don't know if people realize the beauty of this derivation. It's really, really satisfying results. Now, we know that the real Bitcoin did this, but it's really follow almost like an attractor, the most likely path. It didn't even go to this green region. Every time it deviated too much, it wanted to go back. It's a really cool result. Now, you can use then these to make projections to the future, because basically now we know that this is what Bitcoin has done from early on, so we can expect that it will continue to do this, and so you can make projection for the future. Here I made projection. Everybody's interested to know what happened at the end of the year. So basically, 200K is in the book. It's possible, but it's very, very unlikely. It's one of these very unlikely paths. We could even go down to 80K. This gives basically equal weight to going up and down. You could correctly say, well, in a period like this, it's more likely that we go up than down. But, if you consider it equal, then 80 or maybe even 70 is possible, but unlikely. I created some trading view indicators where I color code the different areas in terms of how likely they are, and I will show you in a moment. Now, this is what, I don't know if Stephen, I show you this result. I don't see you, Stephen. Are you there? Yeah, I cannot hear you.
Yeah, I was muted. I'm here.
Okay, so this is one of the latest results that I think I didn't show last time. I think up to here basically was kind of a summary of what we did last time. Let me go back to the full screen mode. I took, so basically this comes from this graph, right? So before I show you that graph, I plotted this mu, and you can see how incredibly stable mu is. So basically, yes, it's oscillating, but by just visual inspection, you can see that it's basically oscillating around this red line, and that red line is 5.91. That is very familiar. It's basically the slope that we get by doing regression, and it's simply oscillating. And notice, even early on, because sometimes regression, if you fit regression only on the first few data, you don't get a good, you don't get the power law easily, because the data was dominated by the bubble. But if you do it in this way, you can show that mu was there, so the power law was there from day one, from when we get the first few data. It's really remarkable, right? Bitcoin has done this power law stuff from day one. And, we don't have the first year, unfortunately. We have only a few transactions. Since we started to get data, that is basically 2010, Bitcoin has done the same thing. And is oscillating now. It's also a cool way of identifying bubbles. Basically, the way to understand bubble is that when you shift it to higher value, that makes sense. So that we found these also with the other investigation. So basically, it's like a general shift towards higher returns. And then it's compensated when we go down and we have a bottoms where we go in the other direction, right? Where basically we have losses that are similar to the gains. And so in average, basically we stay here. This is the average value of all these values, right? I didn't got this from the fitting, regression fitting. I got it from just averaging all these mu's. And you can see it's simply oscillating around that. And this behavior didn't change. Now we could do more sophisticated, maybe doing a moving average or other things like that. But it looks like, just looking at it, looks pretty stable and basically similar behavior, right, over the years. Now you can look at how wide the distribution is, and basically it's this parameter sigma here, and this parameter sigma has almost like two regions. So there was this region up to 2017 where, I don't know, maybe the average value was around 50 or something like that. So that means plus or minus 50 relatively to that 6, right? And again, yes, there is, so again, the bubbles are characterized by two things, both mu shifted to higher value, but also there is more spread, there is more variance. That makes sense. And then something strange happened in 2017 where that value started to go crazy. It reached a peak and then it kind of settled around 75. And again, it stayed stable over the years. Yes, with oscillations, but in average is around 75. And it has not changed over the last years. And this is what this graph also shows, that I found it's probably one of the most impressive, remarkable. It should be viral, but because nobody understands this stuff, the post got 50 likes or 60 likes, when there are posts that get 1,000 likes that are completely trash in comparison with this. This graph basically shows the distribution of these values from 2017 and 2021, and then it compares it with the last 4 years. And what will you say, Stephen, is that, I mean, I don't want to put you in a better spot, but do you agree with me? It's basically the same distribution, right? Statistically, they are on top of each other.
Those are the same. Those are the same,
It's
yeah.
absolutely the same.
What are the soft lines there?
The soft line is the real data, and the continuous line.
Oh, soft line is the real data, and those are
fitting models,
the T-location fits.
T-location fitting.
Okay.
The best fitting for that distribution. So both the real data, and so black is the real data, the distribution, the histogram for the real data, 2017, 2021. Purple, I think, blue, I think is the best fit for theoretical fit for the distribution. And there is an excess here in terms of the distribution. Needs to be understood why there is this excess, but in general, it's pretty good fit. Like, if you calculate P, it's like 0.0000. It's really, really, really good fit. And even if you don't care about the fit, you can see the real histograms are on top of each other. It's the same distribution. It's remarkable because people think Bitcoin changed, it did different things, so maybe it's not it did exactly the same thing, at least for the last 8 years. I'm not showing here the previous data because I could show it. Maybe I can add it. But with the distribution, we'll have the same mean, but it's a little bit less spread. Strangely enough, there is more spread. And now that we associated latest data with less volatility, but I think it's because the returns are going down, so it looks like there is less volatility. But actually, if you express it in terms of slope, the volatility actually went up since 2017 and then stays stable. It didn't change. If if you are thinking in terms of slopes instead of returns, the volatility has not changed for the last 8 years. That is, like, everybody should know this. Like, banks, investors, sailor. It's a more, and this is really, it's not like some silly regression. Regressions are not silly, but this is really the core of the statistical behavior of Bitcoin. It's remarkable. Don't you think? I'm almost shocked by this graph. Do you have any comment, Stephen?
Well, the way I've been thinking about it is that the core volatility has not changed, and the bubble volatility has been coming down. And you expect, with the power law, the total volatility to drop is the derivative, right? Which is
Right.
one power index lower.
So if you express it in terms of returns, the volatility will go down because the returns are going down.
Well, so right.
But if you express it in these corrected returns, corrected by the decay in time, then it's nothing changed. So in other words, a lot of the change in volatility is due to the diminishing returns.
Mm-hmm.
But if you correct for diminishing returns, then nothing has changed. Bitcoin has behaved. And you say, well, what about the bubble? The bubble cancel. Basically, in the end, everything that happens in the bubble cancel each other, right? Because you go up, when you go down, the two kind of cancel each other. And all what remains is the power law behavior that is nothing else than basically oscillations around that average value. And from a statistical point of view, everything you need to know, it's contained in that distribution because it tells you how big the tails are. Now, we can look at the other parameter that is new, that tell us how heavy tails are these distributions and these. So beside this huge big spike, again, something weird happened in 2017 that made spike mu, and sigma. But then after that event, we went down, and now it's still very stable. Now it's continues to be stable. So basically, it's the same distribution, at least for the last 8 years. And from an average point of view, it's the same distribution since 16 years, just a little bit fatter now than before. It is also counterintuitive because most people will think that the volatility decreases, but if you take out that decay due to the power law, then actually stays the same. So basically we can understand Bitcoin as these oscillations around the power law, that is the stochastic behavior, and a deterministic factor that tell us how the returns are diminishing in time. It's a really cool result. And it's weird that we have this deterministic factor that is so precise, that Bitcoin follows actually an equation. And this is another graph that shows this, right? So here I'm taking an average over a moving average over 1 year, 1 years, yes, for this quantity mu. And you can see it's simply oscillating around the average of 5.9. Mm-hmm. And these are the returns that are decaying. The returns are decaying. If you divide by that equation, you don't even have to know what n is, because all of what you divide is log of t plus 1 over t. Mm-hmm. And if you divide by that, you stabilize these guys. Now these guys don't show anymore this decay. They are simply oscillating around an average value. So basically you found, it's one of the holy grail of physics to find invariant quantities, right? Like energy, momentum, etc. Quantity that conserve. Here, they don't conserve exactly, they conserve in average, right? But it's still a stable quantity over time. But it's pretty amazing. Do you have any feedback about that?
Yeah, well, they don't conserve precisely because there are sources and sinks that are human energy.
Right. It's
Right.
it's
Yeah.
it's a strange
Yeah.
combination
Yeah.
between deterministic factors and stochastic factor. They
Mhm.
combine together. It's really cool. And what I did also, I will show you live because it looks better if I show you live. Okay, I'm going to reshare these. I did two things. So I created two indicators. One is this indicator that shows the slopes. So these famous slopes that I'm talking about are these green lines. So these are the daily slopes. Now I'm averaging them here over, I think, 10 days. But so let me show you what happens if I do not average them. So this tells me how much I can average. No, so let me do it here. Yeah, slope vectors, these ones. Actually, I'm using 20 days. But if I average over one day, why does it change? Oh, yes. No. Slope average interval. This should be it. Let me, I think it's stuck. No, let me refresh it. Okay, let's see if now it works. What I want to show you is how these vectors look like if we choose one day instead. Yeah, it looks crazy, right? Because basically every day we are oscillating, right? Sometimes and here green means not necessarily positive, but a bigger slope than the power law. Red means a slope that is lower than the power law. So it's this crazy dance, right? From higher, lower, higher, lower. It's crazy that this guy average to 5.9. They give us the red line. They give us the power law. When you average them, you get the power law. But you can show them if you do an average of their behavior over 10 days, you get something regular. Basically, you identify times when we go down, times when we go up. It's like a magnetic field, right? We are field
Yes.
lines,
Yes.
like field lines, where
Yeah.
and the field lines push the price up and down, but along the power law. It's really incredible. And then I did a Monte Carlo simulation using this, basically, the distribution that we have observed, and you can project it anytime you want. I project it at the end of the year. I have a table that basically tell you how likely it is to get different value. So, for example, 200,000 or higher is still in the books. Basically, just few percent, like 3-4%, less than 2% total chance that we go there. It's more likely, like 160 is not impossible. It's close to 7%. The most likely value, highest value by the end of the year is around 150, something like that. And again, the median here is the power law. Here I'm showing this quantity that is mu. And again, look at how stable this guy is over the entire history of Bitcoin. So even if I go, see, this is the entire history of Bitcoin. Even if I go early days, all what this quantity did, even 2010, I will have to scroll all the way to 2010. What did I do? I closed it. No, I think I closed it. Sorry for that. I pressed the wrong button. Yeah. In fact, this actually allowed me to show the other thing I wanted to show you. So the blue line, look at this blue line, how stable it is over the entire history of Bitcoin. I can go all the way to early days, and it's simply oscillating around that value. It's really the most stable parameter that we have.
Mhm.
Yeah. It's exactly like that, continues to oscillate. Now, let me see if I, yeah, so this is where we are. What is this? Which date? 11, 10, right? It's still oscillating around this value. So it's the most stable value we have. Now, what did I do? The next thing I did, by the way, this blue line is kind of like an adaptive power law that calculates the power law using only previous data up to that point. That is cool. Or this, while the red is based on all the data up to now, right? Anyway, so what is this yellow line? The yellow line, so the blue line, I'm using an interval of several days. I don't remember what it is, 20 days or whatever, right? And then I calculate the statistics. That is basically, so it's almost like you're seeing this distribution from the top, right? Every slice here, every day, you're going to have a distribution based on the behavior over the last 20 days. And you're seeing one sigma above and one sigma below. So basically, it's kind of a measure of how wide the distribution is. And some days it expands. Look what happens during a bubble. During a bubble, mu goes up. There is more variability because this becomes wider. So it's also a way of identifying where the bubbles are. But the relevance of a wide curve, the reason why I cannot draw too many of these is because TradingView has a limitation of many of these lines you can draw. And so it just draws the latest ones. But the yellow is the same quantity mu, but now calculated over just a smaller period of time. Let me show you this. I'm going to take out the slope vectors. And it's really cool because, so this is the same value, right? It shows the more immediate behavior of a distribution calculated over, again, using t-location scale instead of Gaussian. And I'm calculating mu over a few days, like 5 days, for example. And so it catches the sudden changes, right? So, for example, right now, because we're having a little bit of an upswing, we are above the power law, right? We are there. We are 39 when the power law is 5.9. And the intersection between this yellow line and the +1, -1 sigma give us these red and green dots. And you can see where these red dots and green dots are kind of local minima and local maxima. So you can actually use it. I have a version of these where I convert it into a strategy where you can put buys and sells. You could do with future contracts, for example, instead of selling your Bitcoin, right? You could buy future contracts, use margin with your Bitcoin, and then whatever you gain, you can buy more Bitcoin. And it's a strategy that gives us 77% win rate and 3.6 profit factor. That means basically every time you win, your wins are almost 4 times bigger than your losses, and you win 77% of the time. They are relatively rare, mostly because we are doing daily, but we can try hours, etc. But so basically, different from other TA indicators that people use and so on, this one is based on intrinsic properties of Bitcoin, and it catches both the long-term behavior and the short-term actions. And it's really interesting to see this, how everything fits together. Independently from trading is basically telling you, okay, we are expecting a correction up, we are expecting a correction down. And if this is what Bitcoin is going to do for the next 20 years, without crazy bubbles, simply oscillating around the power law, I'm okay with it. I'm open to it. I'm not against it. Okay, yeah, this is my presentation. Any comment on this, Stephen?
Oh, it's quite interesting. It's I would say it's elegant, and in terms of building an indicator, it's rather straightforward. You have that distribution. You know that that's the right distribution.
Yeah.
And then you sample that.
Exactly. Yeah. So anytime with the local changes are too far away, basically 1 sigma, then there is going to be some correction, mm-hmm. and in both directions. And so it's really cool. It's also theoretically a demonstration that is exactly what Bitcoin does. It likes to oscillate around this power law level, the slopes, and if it deviates too much, it wants to correct. And it's like a spring. It's a spring that is oscillating back and forth, back and forth. If you push it too much, it wants to go back to equilibrium. And it literally has done this for the last 8 years. It's unbelievable. Anyway, I don't think we have many. Fred is actually watching us. Hi, Fred. How's it going? I don't know if he has any questions for us, but and anybody can ask questions. Otherwise, if we don't have any questions, we can call it a night or a day. I think we cover a lot of interesting material.
Okay, thank you everyone for joining.
This guy, I recognize him. He has a weird name, but he's one of our most faithful followers. He's here often. Yeah, I like the analogy too. It's a very interesting analogy, and also I like the fact that he gives us a chance to talk about physics and kind of do a little bit of outreach for physics, but at the same time we tie it to Bitcoin. And this analogy, they seem arbitrary, but actually, if you think about, they are really valid. Maybe not from a formula point of view, but at least qualitatively, they are very good because they kind of make you think about processes that are basically universal. We use this word in physics, universal, when we see many different phenomena behave in a similar fashion. Okay, guys, if we don't have any questions, then we will close here and we will see you next week. Bye, everybody.